Hello, welcome back to Math 152. Continuing on section 3.2, and we're going to talk about the empirical rule and then Chebyshev's inequality. What that will do is we're going to take the values that we have learned how to calculate in the previous part of this 3.2. We're going to take the mean and the standard deviation and basically use it to visualize how the data is centered around the mean. Okay. So put that here. Many histograms have a single mode near the center of the data and approximately symmetric. Such histograms are often referred to as bell-shaped, and in fact, we're going to see this a lot, and we're going to start seeing that this is pretty normal the way data is distributed in nature. And we're going to start calling this bell-shaped curve the normal curve. Okay, so basically that bell shape comes from, here's the frequency of our, if we do either the classes or the data values, and here's the frequency. They're mostly centered around that mean. Here's the middle of it, and then some spread out from here. So if you kind of draw here, it looks symmetric, fairly symmetric. Naturally, there's some pieces missing, but it's okay. We're going to approximate this as a bell-shaped curve. There's the curve. I'm going to call it normal as we go forward. Okay, and it turns out if our data, we do a graph, we look at it, and we can see that it's fairly symmetric. It does have this bell-shaped curve. There's some things that we can say about it based on the mean and the standard deviation, and calculate how much of the data, how much of the data points or the number of data points lie within some of these standard deviations. Okay, so this is the empirical rule. I want you to make sure you take this down carefully. We're going to see this throughout, and we're going to expand on it, continue to expand on it throughout the semester. When a data set has a bell-shaped histogram, it is often possible to use the standard deviation to provide an approximate description of the data using a rule known as the empirical rule. What does it mean by the data? It lets you know where these data lie. So what's the values of it close to the mean. Approximately 68% of the data, here's the empirical rule, all of this stuff is the empirical rule. Approximately 68% of the data will be within one standard deviation of the mean. So if I had 100 data points, so let's keep this easy to calculate. If I have 100 data points, let's say the mean is 50, one half of it. I got 100 data points. A standard deviation of 10, so between the mean, which is 50, one standard deviation, which was the 10, between 40 and that 60, 68% of those numbers, or 68 of the numbers out of 100, is going to lie between those 40 to 60. The mean, which was 50, between plus or minus the 10, which is the standard deviation. So that holds for no matter what number of data points you would have. You could do the same calculation, 68% of whatever number that you would have. Now within two standard deviations, so back to my example, if we had a nice easy calculation, I had 100 numbers that I've worked on. I've got the mean and it turned out to be 50. The standard deviation was 10, so 50 plus 2 times 10 to 70. 50 minus 2 times 10, which is 30. Between 30 and 70, 95% of the data, or 9.95 times the 100 data points, 95 of those numbers in general would be between the 30 and the 70. And then finally, almost all of the data would be between 3 plus or minus 3 standard deviations of the mean. Okay. So 50 plus 3 times 10 is 30. Between 80 and 20, between 20 and 80, almost all of these things in other books, we'll see it later, something like 99.7%. So almost all of the data, 99 of the values would be there. Okay. So that's the empirical rule. We can use that to kind of get a quick, if I'm just giving two numbers, the mean and the standard deviation, I can determine what the range is and how the data is laid out. Okay? The following table, here's an example. The following table presents the U.S. Census Bureau projection for the percentage of the population age 65 and over for each state and the District of Columbia. Use the empirical rule to describe the data. Okay. So I would need to copy this down. A very quick way, I would copy it down into Excel. I would use the average function to find the mean, the standard deviation. This would certainly be projection sample data. So we would do the sample standard deviation, and then we could tell how it lays out. So if I did these things, and if I plotted them out based on each one of these, between these ranges, 8, 9, 10, 11, 12, 13, 18, here's the frequency of those numbers. Okay, so we see it's reasonably symmetric, not perfectly, but it's fairly reasonable that we can use the empirical rule. Okay, so we first note that the histogram is approximately bell-shaped, and we may use the TI-84 plus calculator to compute the population mean, the standard deviation, and here's the TI data. We'll go over some Excel data as well if we do it in Excel to get the mean, and here's the population standard deviation. So they're going to use this as population data of the U.S. Census. So the mean minus the sigma, that is one standard deviation away from the mean. Here's the standard deviation, there's the mean. And here's the mean plus one standard deviation up, the mean plus one standard deviation. So between these two values, approximately 68% of the data values would be between here. So they're saying they have the census data, they're considering that population data, that would be a lot of numbers, but 68% of them would be between those two values. What about 2? If I did the 2 times this, that's 2 standard deviations out, 2 times the standard deviation. 13.249 minus this, that would be 9.88 would be the lower end. The mean plus 2 standard deviations, that's 2 sigma. 2 times the standard deviation, 16.61. Now we get to use that second empirical rule data, the 95%. The 95% of the numbers would go between 9.88 and 16.61. If I went to 3 standard deviations, mu minus 3 sigma, there's the mean, the same standard deviation, but I'm multiplying it times 3 because I'm subtracting, adding to get my plus 3 sigma. Those are the values 8.20 and 8.30. Almost all of the data values are between 8.20 and 18.30. There's only something like 0.03% outside of that window. So that is the empirical rule, and it can only be used, remember our first thing that we did when we started this, is to say, is it approximately bell-shaped? If it's bell-shaped, we can use the empirical rule. What about if it's not? Then we have to go and use Chebyshev's inequality. Okay. Chebyshev's inequality is not as exact as the empirical rule, but it gives us a rough idea. So when a distribution is bell-shaped, pull down here, the empirical rule to approximate the proportion of data within 1 or 2 standard deviations. Another rule called Chebyshev's inequality holds for any data set. It certainly works for the empirical rule as well, but it doesn't give us the exactness that the empirical rule would use. So we can always use Chebyshev's, but it wouldn't be as good as the empirical rule if it's symmetric, because we know something else about the data. In any data set, the proportion of the data that is within k standard deviation of the mean is at least 1 minus 1 over k squared. Now, k is equal to 1 standard deviation. This is 0. 1 minus 1 over 1 squared. 1 times 1 is 1. So this is just 0. So it doesn't really give us any information about k is equal to 1. Okay, it just says the minimum is 0, so that could be more than that. So the proportion of the data set that is within case of the mean is at least. So the least is 0% for the 1, it doesn't give us any useful information. However, for 2 or 3, it does give us some information. So if I set 2 equal to that in there, so that's 1 minus 1 over 2 squared, 2 standard deviations. 1 minus 1/4 gives us the 3/4. 3/4 is 75%. So no matter what the data set, if I've got the mean and the standard deviation, but for 2 standard deviations out, at least 75% is going to be between plus and minus 2 standard deviations of the mean. And if we do this number for 3, 1 minus 1/9, that's 8/9, and this number is like 89%. 89% of the data are within 3 standard deviations. At least, and I'd like to point out that at least again, it could be more. All of the data could be within, the 1, it could be within the 2, or with the 3. They could all be there, but at least the minimum would be the 75% for 2, 89% within plus or minus 3 standard deviations. So this is a good useful formula as well. Works for anything, but that empirical rule, if you've got the additional information that it is bell-shaped, normal distribution we're going to talk about, that we can use that empirical rule, and it gives us a better estimate. So as part of a public health study, systolic blood pressure was measured for a large group of people. The mean was 120 and the standard deviation was 10. What information does Chebyshev's inequality provide about these data? So so we can only start that get us any useful information at starting at 2. So here's our x bar minus 2 standard deviations. Here's x bar plus 2 standard deviations. There's the 3 standard deviations. 3. So here is our plus or minus 2, plus or minus 3, but what percentage of data? That's what this is. That's what Chebyshev's is going to give us next. So at least 75% had systolic blood pressure between the plus or minus 2 standard deviation between 100 and 140. 75% from Chebyshev's. If this had been bell-shaped, what would we have got? Between plus or minus 2, we'd have the 95. Plus or minus 1 would have been 68. So this had 75, at least 75. If it was we could do more. Okay. At least 8/9 to 89% had systolic blood pressures between 90 and 150. That's the least. It could be more. 99.7 if it was symmetric data. Again, at least here for 75, at least 75. It could be more, and for us, 95 between plus or minus 2 if it had been symmetric data. So there's one last way that we can compare data and how spread out it is, and this is called the coefficient of variation. So if we had 2 data sets that were maybe the same kind of description between 2 states, we could use this coefficient of variation to compute the mean and the standard deviation and compare these numbers with this calculation, and we could compare those 2 different sets of data. Okay? And this is the coefficient of variation. It basically tells how large the standard deviation is relative to the mean. So the coefficient of variation is divided by taking the standard deviation and divided by the mean. So National Weather Service records show that over a 30-year period, the annual precipitation in Atlanta, Georgia had a mean of 49.8 inches with a standard deviation of 7.6 inches. And the annual temperature had a mean of 62.2 degrees Fahrenheit with a standard deviation of 1.3 degrees. We want to compute the coefficient of variation for precipitation and for temperature, and which has a greater spread relative to its mean. So we're comparing two different data sets. They have, they have some things in common, but they're talking about two different things, but we just want to do relative spread between the two. So we're going to do the coefficient of variation for the precipitation, coefficient of variation for the temperature, and then just compare that. So for precipitation, the standard deviation of precipitation was 7.6. The mean precipitation was 49.8. So this is now unitless. It's like I'm dividing inches divided by inches. That would be just a pure number, 0.15. And for the temperature, standard deviation for temperature divided by the mean temperature, 1.3 degrees divided by 62.2 degrees. The degrees divide out, and that's a pure number, 0.02. So here the standard deviation is wider given that mean temperature or the mean precipitation than what it would be for the temperature. So this has a greater spread than this relative to each one of its means. So the CV for precipitation is larger than the CV for temperature. Therefore, precipitation has a greater spread that the range of the data was larger. Okay. So that basically finishes up for 3.2. This is from all of the objectives that we've worked on. We found out how to compute the range of a data set. That's the max minus the min, the largest minus the smallest. The notation for population variance, that would be sigma squared. Population variance, the sigma squared. The population standard deviation, that would be sigma. Sample variance, S squared. Sample standard deviation would be the S. How to compute the variance of the standard deviation for populations and samples. Go back and review the formulas. We're going to work on those in class. We'll do some calculator work, Excel work to see how to get those values and by hand. How to use the TI-84 Plus calculator. Doing the L1. If we do group data, we're going to put the midpoints in L1 and then the frequency in L2. And then that'll do, that basically sets us up for doing the one-bar statistics to get the mean and the standard deviations. How to approximate the standard deviation for group data, the midpoints. How to use the empirical rule to describe a bell-shaped data set. We've got a bell-shaped data set. We've got the 68, 95, almost all 99.7% for 3 standard deviations. How to use Chebyshev's inequality to describe any data set. If it's bell-shaped, we're certainly going to get a better result estimate with the empirical rule, but for any data set, we can use Chebyshev's inequality to find out those values. From there, the 75% and then the 89% for 3 standard deviations. And then how to compute and interpret the coefficient of variations, relative spread based on 2 different data sets that may not be the same information, it may, but we can tell differences in area, location, or type. Okay? So I hope you found that helpful. We'll see you next time. Have a good day.